And so now comes the question, what is a black hole? A black hole is the most bizarre object that you can imagine, and it is something that you want to stay away from too. A black hole has no size, unlike a neutron star. It has no size, but it does have mass. And it has a lot of mass. 3 times the mass of the sun, 10 times the mass of the sun, 100 times the mass of the sun. So it has mass, but it has no size. We identify around the black hole a sphere with radius r, which we call the event horizon. Imagine you are at the event horizon and you want to get away from the black hole. What kind of speed do you need? You should be able to give me that answer immediately. The escape velocity must be 2 mg divided by the radius of that event horizon. In other words, the radius of the event horizon itself equals 2 mg divided by c squared. If you tell me what m is, I will tell you what the radius of the event horizon is. I went a little fast here. I skipped an important step. V is the escape velocity from the event horizon, which is at a distance capital R from the mass m. So we see that here. Now this escape velocity can never be larger than the speed of light. So the maximum value possible is c. And if now you look at this part of the equation and you take the radius on one side, you'll get that the radius of the event horizon equals 2 mg divided by c squared. And that's how I found that equation. Sorry that I went a little too fast. If m is the mass of the Earth, the radius of the event horizon is 1 centimeter. If m is the mass of the Sun, the radius of the event horizon is 3 kilometers. If m is 3 times the mass of the Sun, the radius of the event horizon would become 9 kilometers because it scales linearly with the mass. If you were inside the event horizon, you could never escape the black hole because you would need a speed which is larger than the speed of light. Therefore, you can never escape from inside the event horizon. Nothing can get out of it. Not X-rays, no radio emission, no light, nothing. Once you're inside the event horizon, you've had it. You cannot escape it. And so the question now that comes up, can we see X-rays from a black hole? Because if nothing can come out of a black hole, how can we see X-rays? And the answer is yes, we can. Because as long as the matter that swirls in is outside the event horizon, it would still be very hot, because gravitational potential energy would already have been released. It would be very hot, and it would emit X-rays. So we can see X-rays outside the event horizon. You will never see pulsations, because a black hole has no surface, like a neutron star. So there's no such thing as 2 hot spots which rotate around. And so now comes the problem for astronomers. How can you determine the mass of the accretor if the accretor is not a pulsating neutron star, but if the accretor is a black hole? Well, you can only now measure the Doppler shift of the donor, because the donor in general is quite well visible. It's an optical star. But you will not be able to measure the Doppler shift of the black hole, no pulsations. If, however, an astronomer can make an estimate of the mass of that donor, then you will find the mass of the accretor. In other words, instead of having the Doppler shift measurements of both stars, the neutron star and the donor star, which gives you the mass of 2 stars, now you have to settle for the Doppler shift of only the donor and the mass of the donor itself. And if you have a reasonable idea of what that mass will be, then you can find the mass of the accretor. And there is a very famous case, that was the first one discovered in the early 70s, which is called Cygnus X-1. Cygnus X-1 is an X-ray binary which has an orbital period of 5.6 days. The Doppler shift measurements of the donor were made, and astronomers, simply looking at the spectrum, at the absorption lines and the structure of the absorption lines and the kind of absorption lines, were able to say, yeah, the mass of the donor is probably approximately 30 solar masses. And with that information, and with the Doppler shift, you can now arrive at the mass of the accretor, and that is, in this case, oh, by the way, there's an R missing in the word accretion there, and that mass turns out to be about 15 solar masses. Now, when this was found in the early 70s, most people concluded this has to be a black hole. It is a very compact object, otherwise it wouldn't emit X-rays in the first place, and clearly, if the mass of that compact object is way larger than 3 solar masses, then there is no doubt in our minds that this is a black hole. Since that time, many black hole X-ray binaries have been discovered. So if I summarize, the amazing thing is, from studying the Doppler shift of binary systems like X-ray binaries, you can derive the orbital parameters, orbital radius, orbital period, the speed of the stars in orbit, but you can also find the masses. And whenever you make a measurement of the mass, when it is a neutron star, when you see the X-ray pulsations, you almost always find that it is very close to 1.4 times the mass of the sun. But in a few cases, you will find that the mass is substantially larger. Admittedly, you have to do without the Doppler shift then of the accretor, but you have to use some other information, and then you can conclude in most cases with pretty good confidence that you're dealing with something like bizarre as a black hole, of which you can only define the event horizon, and you can never escape a black hole when you're inside the event horizon, because that is when the escape velocity would be larger than the speed of light. So this is the escape velocity. If you set that equal to c, then you can solve for the radius of the event horizon, and out of it pops this equation. I would like to show you now a slide of Cygnus X-1, which is the oldest known black hole X-ray binary. I have to lower the screen. And there it comes. This was really a bombshell when this was discovered. I still remember reading that first publication. 2 people discovered this independently, by the way. They came independently to the same conclusion. It's Tom Bolton and it was Paul Merlin. 2 independent groups. All right, here is an optical picture. It is a negative, so you see the stars dark and you see the sky bright. And right here is the star that is Cygnus X-1. It's the donor. It is a very large star, a supergiant, huge radius, and it is believed to have a mass of 30 times that of the sun. You see here a close-up. This is not the companion, believe me. This is just an image of that star. The position was hard to get an accurate position. Various groups made a major contribution to finding the position. One of the rocket flights of MIT found a position that is quite precise, and there was no doubt later, when the orbital period was found of 5.6 days, there was no doubt that this was the X-ray source. And so this is a system whereby you can only see the donor in the optical light. You can measure the Doppler shift of the donor, and by looking at the spectrum of this star alone, you come to the conclusion that the mass must be about 30 solar masses, and then you can argue that the invisible X-ray source must be a black hole.